All right, so hearing none. Last time, what did we end with?
E to the 8th.
We were doing exponentials of matrices to solve differential equations. So it's sort of late now because you guys have already done your web work problem. So I will do an example. So suppose I want to solve x dot or prime, I don't care. A equals A times x of t, where A is the matrix 7, negative 6, 9, negative 8. And I'm given the initial condition that it's at time 0, we're at, oh, I don't have it in my notes. That's good. So I'll make one up. Great.
The origin would be harmless.
Now the origin would be very boring.
Oh, okay.
It wouldn't move anywhere. Right? Because if you have a linear differential equation, but this is actually important to understand. Suppose x of 0 is the 0 vector. What's the derivative then at 0?
0.
So basically it sits there and it doesn't change, and you could say, well, maybe a third derivative becomes non-zero and it starts to move. Well, no, that's not going to happen because of this linear equation. So if you start, this is the same thing you know from calculus, that if you have an exponential growth and you have a 0 population, it stays 0. So an initial condition of 0 would be highly boring. Okay, so find x of t here. So what's the strategy? Diagonalize. So strategy, hope A is diagonalizable. And then what we talked about last time, and I'll confirm this in a little bit in a few minutes, we said x of t is going to be given by multiplying by the exponential of t times the matrix times your initial vector. So remember we said this was analogous to the decomposition of the solution of a difference equation into what I was saying are sort of normal modes. So if A is diagonalizable, I haven't yet gone through all the details with exponentials, but I will in a minute. Then this is going to tell you that e to the ta is given by p e to the t lambda p inverse, just like what we were doing with powers on Friday. So we'll get p times the matrix of diagonal exponentials and then you multiply by this vector of scalars, which is given by doing the inverse times your initial condition. So what you're going to get then, and I believe I said this on Friday, is remember the columns of P are your eigenvectors. So you're going to get your first eigenvector times some constant, the first entry of this guy, e to the t lambda 1 times the first eigenvector plus the second constant e to the t lambda 2 times your second eigenvector, and so on. And this is truly what in physics and engineering these guys are called the normal modes, because you're writing every solution in terms of these basic solutions which have eigenvector and eigenvalue exponential paired together. So let's do it for our matrix. What are the eigenvalues? What's the characteristic polynomial? T squared
plus t
minus trace plus determinant. Negative 2. So the eigenvalues are
So 1 and 2 and 1.
Okay. Huh?
My one is negative 2. Yeah.
Okay. I thought I heard you say the other thing.
I know, that's what I said.
Okay, so what's the eigenspace? Corresponding to this eigenvector, what are we going to have? We have this eigenvalue, what are we going to have for eigenvector? If we do negative 2, that means we add 2 to each diagonal.
2, 3.
So we're going to have 9, negative 6, which is 3, negative 2, so 2, 3. Should work. So you guys should be doing enough practice now. You can do these pretty much in your head for 2 by 2s. For 3 by 3s, nobody can do that.
Yeah, 1, 1.
Now I'm going to get 1, 1. So what's my P matrix? 2, 3, 1, negative 1. Whoops, 1, 1. P inverse. So why do I need P inverse? I need it to get the C.
So it's going to be,
So it's negative 1 times.
yeah, it's going to be negative 1. Yeah.
So there's P inverse. So the vector of constants is going to be P inverse times my initial vector, which I made up randomly. Negative 1, 1, 3, negative 2 times 2, negative 1. So what do we get?
Negative 3. 8.
8. Perfectly lovely numbers. So our solution is x of t equals this constant times exponential of negative 2t times the first eigenvector plus this constant times e to the t times the second eigenvector. There's the solution. And you should be able to actually check, if you actually write it out, that it satisfies the differential equation. I'm not going to take the time to do that. I mean, just as a mild check, notice when you put in t equal to 0, these become 1. And so you're going to get negative 3 times 2 is negative 6 plus 8 is 2. And then you can get negative 9 plus 8 is negative 1. So the initial condition at least is checking. It's not so surprising. Okay. All right, so I want to talk today about what the matrix exponential really is and what you do when things aren't diagonalized. And then we're going to see, so what's your, okay, so before I do this, so recall that the definition is that we took the power series for e to the x, which converges to e to the x for all real numbers, and we said, let's plug in a matrix and do the exact same power series. The first reasonable question is, why should that even converge?
So factorial goes faster than.
But when do you want the norm less than 1?
No, so recall, e to the x, this series converges for all real x by the ratio test. Those of you who have taken 3100 or 2410 will know that in fact on any closed interval on R it converges uniformly, which is important for lots of things. But in fact, it also converges for all complex numbers as well. because the ratio test really is about putting in complex numbers and not real numbers. So in fact, I'm going to say here, indeed, for all x and c. But why can you put matrices in?
Well, if it's diagonalizable.
It's not.
Okay.
So why should it be that if you put in a random matrix and take its powers with the k factorial, that that's going to converge to an actual matrix? Summation thereof. Mm-hmm.
Can we put something like the diagonalizable like format if we use complex numbers?
No. Not necessarily. I mean, I'll talk about examples in a minute.
Could we use the norm of the matrix?
Yeah, so I gave you the hint on Friday, which is from chapter 6. We know that a series of vectors converges if and only if it converges absolutely. Now, you're going to complain that a matrix isn't a vector.
So technically we split, right?
That hasn't stopped us before.
Exactly. We talked about how the matrices form a vector space. Where you're just thinking, if you have n by n matrices, you just think of them as being a vector with n squared coordinates. And we've talked about the norm of a matrix being the max of A times X, when X is a unit vector. And with respect to this norm, you know that forget what that is later. So recall that the norm of a product is less than or equal to the product of the norms. You've used that in homework. So that means that if you take the norm of a power of A, it's at most the power of the norm of A. So therefore, if you take the sum let's just say you go to sum capital K here. You take the partial sums of this series, and you go out to sum capital K. The norm of the sum is at most the sum of the norms by the triangle inequality. Which is at most norm to the k. So now it's just looking like the partial sums of the plain old exponential series with a real number in there.
And that converges.
And we know that series converges, so these partial sums are all bounded by e to the magnitude of a. And so, because you have an increasing, well, so let's see, so the sequence of partial sums right, so what we proved in class was if it converges absolutely, then the series actually converges. Well, we know when you put in absolute values here and take norms, we know it converges because of a series of positive terms being bounded above by a convergent series gives you a convergent series. So therefore, absolutely convergent. And we proved. Yeah, so this part is sort of irrelevant, actually. The series converges.
You said that goes the other way, because conversion implies that.
No.
I thought he said.
Oh, for a series.
No. I mean, you know that from calculus. Convergent does not imply absolute convergence.
Yeah, you could.
Oh. Oops. Sorry. I didn't understand you were saying. I wrote that. Yeah. Right. So we, yeah. So that's bad. Let's just put it again there. Yeah. Okay. running out of my quota of mistakes. All right, so what's an example of a matrix that is not diagonalizable?
Projection matrix.
No, projections.
Wait, sorry, that is diagonalizable. It's diagonal.
A
No.
rotation matrix.
Hmm?
A rotation.
Rotation. So what happens if we do a matrix that's like a 90-degree rotation? So I actually talked about this guy when we were talking about eigenvalues. Do you remember what we discovered the eigenvalues of this thing were? Plus or minus I. So if you were going to allow yourself complex matrices, you could diagonalize using complex numbers. And in fact, I'll do that in a minute. But let's just see what happens if we try to take e to the t times a. And put a t in there because you'll see, first of all, if you were solving differential equations, you'd want that. And secondly, it's more interesting with the t. So I would ask, what happens if we do this rotation, but instead of rotating a whole 90 degrees, we rotate t times that? Any amount. So let's see. I guess I'm supposed to take the sum. I'm going to take the sum of kth power of this, well that's the kth power of t, times the kth power of this guy, over k factorial. Now think about this geometrically. What are the powers of a 90-degree rotation?
Rotations.
Specifically what?
By 180 and 70.
And then you're back to where you started. So in other words, a to the 1 is a. Well, let's be stupid here. Convention, by the way, just with always is the case with Taylor series. When you have the 0th power, the convention always is 1 normally, but now we're doing matrices, so it's the identity. A to the first, a. What's a squared? It's rotation through pi minus rotation through pi.
Minus I.
What's the matrix?
-1, 0, 0, 0, -1.
Yeah,
In other
you're
words,
right.
it's negative I. What's a cubed?
Is it negative A?
Negative a. What's a to the 4th?
I.
Back to a again. I'm sorry, back to I. Right? We just cycle through again. So this thing is going to be giving me 4 different kinds of animals. So if I start off with k equals 0, I'm going to have the identity matrix times t to the 0 over 0 factorial. Then I'm going to have t times a, and k is 1. T to the 1, matrix A over 1 factorial. What happens when t is 2? I have t squared over 2 factorial times a squared. And then I'm going to have t cubed over 3 factorial times t matrix cubed, which we said was minus a. And I'm going to have t to the 4th over 4 factorial times matrix to the 4th, which we said was I. So what's going to happen here?
That added together all of
You
the
can
like even for
prove the coefficients of the different matrices.
So let's pull out the ones that have identity in them, and then the ones that have A in them. What do you get?
1 minus t squared over 2
Plus T squared.
To the 4th, or 4 factorial. You can probably guess what comes next. Minus t to the 6th over 6 factorial, and so on. Is anybody ringing a bell yet?
Isn't it like
Sine.
cosine or
Yeah.
sine?
Sine or cosine?
It's one of them.
Which one's even and which one's odd?
So that's sine.
Cosine.
cosine is
Cosine.
What about this one? T minus t cubed over 3 factorial plus t to the 5th over 5 factorial, and so on. This is sine of t.
And so all this works out rigorously. I mean, we're just expanding things and grouping as we wish.
Converges uniformly, absolutely, on any closed interval, so you can do anything you want.
Is that where the,
So
oh,
these
there's
are
thing
supposed
comes
to
from?
look like.
So what's the matrix I'm ending up with? Identity with cosine t,
That's cool.
and A with sine t.
Which is the matrix for all.
So exponentiating this guy with a t is giving you the rotation matrix for all angle t.
Okay.
Now, flip side of this was, you guys were saying the eigenvalue was I, or negative I. So, plus or minus I are the eigenvalues. So we ought to be able to just pretend we're doing linear algebra with complex numbers. I mean, you guys aren't scared of a little complex number.
More complex.
So what are the eigenvectors? Well, I do A minus little I times the identity matrix. Sorry about the I's. I suppose the I's have it. Maybe they don't.
I see what you did
So what do I have? When I subtract little I times the identity, I have this.
Yes.
And so what's an eigenvector? Well, I want somebody orthogonal to both rows. How about this? That's clearly orthogonal to this guy. And if you check here, you'll get negative I squared, so that's plus 1, minus 1. So it works with both of those. And if you do the conjugate, I'm just going to get the conjugate matrix. So the eigenvector, not surprisingly, will be the complex conjugate, so it'll be negative I, 1. So what do we get now if we do our complex trick? I mean, use the diagonal form, right? We'll have A is P diagonal matrix P inverse
Those even linearly independent.
Which ones?
Sure. Can you give me a scalar multiple distance that? Look at the ones. So even working over complex numbers, these are still linearly independent. No. So what do I get here? So I want to say what's E, I want to figure out what E to the A is here.
So it will be P times e to the lambda. P inverse.
So let's put the T's in there. Why not? Okay. Now what's this going to be? P, I1, negative I1. What's E to the IT? I don't know. It's E to the IT. I haven't gotten to that lesson yet.
Does it matter which columns you're?
Did I do it wrong? It should be the same order that I did the eigenvector. So this is the eigenvector for the first eigenvalue, which was I.
You put I.
It's I,
Okay.
right?
So it doesn't matter that we put them in the diagonal matrix.
Huh?
It does, it's just remember, it's, A minus.
A minus lambda I.
Okay, yeah, that's right.
Right, the lambda's little I there. And then P inverse. Well, all right, what is P inverse? 1 over 2I. 1I, negative 1I. so I'm not going to punt this because I want you to see where this gets us. So let's finish this on the other board. What have I got? I've got I1, negative I1, e to the it, e to the negative it, and then I've got so what's 1 over I? It's negative I. Because I times I is negative 1, so 1 over I is negative 1 over I. So I'm going to have a half, and then I'm going to just multiply everybody through by negative I, just to simplify my algebra. So I'm using the fact here that 1 over I is negative I. So what am I going to get?
Negative I.
1. I.
1.
Okay?
Would it be negative 1 on the bottom there?
No. Negative I is.
Oh, yeah.
Yeah, okay. So, what do we get here? Well, let's just be patient and multiply this out. So I'm going to get negative I e to the it e to the it I e to the negative it e to the negative it. Is that right? All right. One more step. What do I get here? E to the it minus plus, right? Negative I times I is plus e to the negative it. I get I e to the it minus I e to the negative it. So I'm sort of conjugating things here. And then I'm going to get the sum here. So I'm going to get the negative of this. And then down here I'm going to get the same thing I had there. So what does this seem to say? I should have done it the other way around. This, a half of this is matching what? Cosine t. And a half of this is matching sine t. And if I had done the algebra the other way around, so this is my fault, instead of doing A equals P matrix P inverse, I should have done it the other way. So this is, what we just showed here is something attributed originally to Euler, but it's not apparently due to Euler.
Great.
So in other words, e to the it is cosine t plus I sine t. So the matrix, capital A, you said was rotating by 90 degrees. That corresponds to multiplying by I. Little I takes vectors in the plane and rotates them 90 degrees. And then you're getting this matrix equation that's saying that these are equivalent statements. Now, if you actually took the power series for an exponential and plugged in IT to this series, you would have gotten cosine t plus I sine t. In other words, for the Taylor series, you would have gotten this immediately. So this is one of the great famous links between exponentials and sines and cosines. This is one of the great mysteries of life. So here it comes in through the linear algebra, giving you the geometric interpretation again that both multiplying by I is rotating the plane 90 degrees, and exponentiating gives you all the relations. All right. Any questions on that?
If multiplied by I rotates at 90 degrees, so would x dot ix equal 0?
Well, what does I mean there?
It's a scalar complex.
So I mean, you have to treat that as actually rotating the vector. You can't just multiply by I and do the real geometry. So you have to take x1, x2 to minus x2, x1 or something, or x1 minus x2, whatever. Sorry. Okay. Other example. What if I took this matrix, which is not diagonalizable? Why is it not diagonalizable?
We can look at the, we can only have one eigenvalue, so.
What are the eigenvalues? Remember, if you have an upper triangular matrix,
Isn't that only 0?
then the diagonal entries are going to be the eigenvalues. So the only eigenvalues are 0, but you only have a one-dimensional space of eigenvectors, because only the first vector gets sent to a scalar mul 0 times itself. The second one does not. So this cannot be diagonalized. There it is in all its glory.
Wait, so we know the eigenvalues are 0. Why does that mean it's not diagonalizable?
Because the only matrix similar to a scalar multiple of the identity is itself. That's homework. So therefore the 0 matrix is the only possible diagonal thing you could have, and that isn't the 0 matrix. So what is e to the TA this time?
It's just 0.
No, it's not.
Maybe there's some nice formula for powers of A.
Yeah. A to the first is A.
Is
What's A squared?
it 0?
Yeah, if you square that matrix, you get 0.
And then you multiply
What's
by
A cubed?
0.
What's A to the fourth?
0. I can play this game all day.
So what's e to the TA? Identity plus do the same power series that we did up there.
So TA,
TA plus t squared over 2a squared.
just all of them.
So all the rest is 0. So e to the t times a is this very interesting matrix now.
Is that diagonalizable?
Again, the eigenvalues are on the diagonal.
Algebra.
So now, what if I took this and put not 0, but a different eigenvalue there? Anybody want to guess what happens now?
Still not diagonal.
Right, still not diagonalizable. But I still would like to know what e to the t times it is. Well, so how are we going to figure out the powers of this guy? They're not all going to be 0.
Split it up into 2. So diagonal plus the other triangular stuff.
So now what happens if you start taking powers of this? So I'm going to call that A, because this is A, right?
Wait, does it just
Oh,
become
but those
lambda
those
times
A's
identity?
go away pretty quickly.
Yeah.
So what do I get?
Lambda squared I.
Plus 2 lambda I A. That's it.
Because the identity matrix in A commute, right? Identity commutes with anybody. So identity times A or A times identity doesn't matter, you just get A with the lambda. And then A squared is 0. Anybody want to guess what A B cubed is going to be?
Well, it'll be that times B, so.
So you multiply this by another I plus A. And again, no A squareds, right? So what do you think I'm going to get for e to the TB?
Well,
Maybe lambda I.
you can split up the I terms and the A terms.
Okay.
So for I,
Lambda to the T.
we'll have 1 plus lambda squared.
No, we'll leave this term first.
T terms.
Lambda t, and then from the b squared I'll get a lambda squared t squared over 2. And then I'll get a t cubed over 3 factorial lambda cubed. What does that look like?
E to the lambda.
E to the t lambda, right? Times the identity. Or lambda t, whatever. And then, what have I got here? How many a's? I'm going to get from the first one, first power, I'm going to get TA. From the second one, I'm going to get 2 t squared over 2. From the next one, I'm going to get 3. Oh, wait, I left out a lambda, didn't I?
Yeah.
T. So this has a lambda in it. Squared? No, single lambda. All right, sorry. I need to rewrite this more carefully. T plus t squared over 2.
Did we do B cubed right?
Wouldn't there be a lambda on the T?
Oh, this has a square, doesn't it? Okay, yeah, we skipped steps too much here. Yeah. Okay. Shouldn't trust you guys. Okay, let's try this again. Lambda cubed. Now what?
Let's make 3 lambda squared I.
And then
0. So lambda a squared.
Because you get a squared over
That's
0.
okay, plus 0. Okay, so what's the pattern? You're going to get the lambdas are one behind here, and you're picking up the exponent. So let's try this again now. So the first term, the lambda, the TB is going to have a t. Then when I do t squared over 2b squared, what do I have? 2 lambda a's. Then the next term, t cubed over 3 factorial, I'll have 3 lambda squareds, and so on. So what does this turn into? How many a's? t. So t plus, the 2's cancel, lambda t squared, or t squared lambda, I don't know.
Oh,
And
then
then
factor out a t.
t cubed over 2 factorial lambda squared. So if I factor out a t, what have I got?
You got e to the t lambda.
I got e to the t lambda. So I've got e to the t lambda times the identity plus t e to the t lambda times a. So this is actually going to come out looking like this. Interesting. So you've got e to the t lambda, e to the t lambda, t e to the t lambda. Those of you who have taken 2700 should be saying this looks sort of familiar.
This looks sort of familiar.
Does it?
I mean, it's always familiar.
All right, so I want to show you now this connection to 2700 differential equations here. We've talked about how you can use systems of differential equations to get a first order equation, but what if I had a second order equation to solve? So I'll have to finish this discussion tomorrow, but what would happen suppose you had a differential equation that looked like second derivative with respect to t minus first derivative minus twice the function is 0. And then somebody told you y at time 0, and somebody told you the derivative at time 0. So in the standard differential equations course, you've learned how to solve these in a mechanical way.
There we go.
But we can be smart, because we know all this when you're algebra. This should remind you of the difference equation we had when we were doing Fibonacci, and ak plus 1 depended on ak and ak minus 1. This is the continuous time variation version of that. Second derivative depends on first and no derivative. So I'm going to introduce a vector that encodes 2 bits of information, just like we did with the difference equations. I'm going to put in y of t and y dot of t, and make that my x. So what differential equation does x satisfy? Well, x dot is going to be y dot, y double dot. And we know what y double dot is because we got an equation. So this is just like what we did with the difference equations. You have y dot here, and then you have y dot plus 2y here, all of t's. Shouldn't bother with the of t's. So this is given by a matrix times this vector. What's the matrix?
0, 1. 1, 2,
2, 1. And so you say to yourself, I wish I could diagonalize. Well, what are the eigenvalues? Well, that's interesting. Look at that. looks an awful lot like this. And those of you who have taken 2700 are used to this phenomenon, but not quite from the same approach. So the eigenvalues are
2 and -1.
and so you can solve. And what do you get? You get that the x vector is going to be constants times e to the 2t times the first eigenvector plus constant times e to the negative t times the second eigenvector. And so in particular, if you look at the first component of x of t, you're going to get that the general solution is in fact some other constant, depending on what v1's first coordinate is, plus some other constant, depending on what v2's first coordinate is, times e to the minus t. There are your exponential solutions coming from our matrix theory.
What we did was?
Just reading off what y of t is. So v1 has numbers in it, and v2 has numbers in it, so I'll get numbers changing my constants. I'm not going to take the time to write this all out because we're running out of time. Now, what would happen if I had this differential equation? Right. Now I get the matrix 0, 1, 1, negative 2. And what's my characteristic polynomial? Uh-oh, I got it wrong. What did I do wrong?
Be just 0.
No, someone's wrong here. What's y double dot? It's negative y plus 2. There we go. So I get characteristic polynomial. These are minus 2t plus 1. Repeated root. Clearly not diagonalizable, because if it were diagonalizable with repeated eigenvalue 1, I'd have to have 1 as the only eigenvalue, so it would be similar to the identity matrix, and it's not. So what do I know? I know that, well, you don't know this, but I'm going to tell you, there is a basis with respect to which A becomes the next best thing to diagonal. You can't diagonalize, but you can get the eigenvalues on the diagonal and something off the diagonal, like a 1. So this is called Jordan canonical form, and if you take more advanced math courses eventually, you may or may not see how to actually do this in general. But now you see we're back to this case. So when you exponentiate this, you're going to get a constant times e to the t times some vector plus a constant times t e to the t. There's this t times another vector. And that's going to tell you that the general solution of this differential equation is some constant times e to the t plus some other constant times e to the t, e to the t. So when in your differential equations course you had repeated roots, they told you by magic that you start putting in powers of t times the exponential. Correct? I'm looking at people that have taken 2700.
Skip repeated roots in my class.
You skipped repeated roots. Did you skip repeated roots?
Added a constant or something.
No.
Yeah.
That's,
T a constant, yeah.
that's what happens, and this is why it happens.
Yeah, we just doesn't magically do it.
Yeah, okay. Now you know where it came from, actually.
If you're literally told that no one knows why.
That's not true.
Yeah.
And I can show it to you another way too, but not in class today. All right, so tomorrow I'm going to finish up this discussion by showing you that sines and cosines are the only solution of the second order simple harmonic motion equation, and talk a little bit about how this differential equation stuff ties in with divergence, and then we will start the last section of the course.